In this video, we learn how to calculate the sum of the first n terms of a geometric sequence. More specifically, we'll learn the formula for calculating the sum, and we'll learn how to use it using the two examples that we have here. Given a geometric sequence or a geometric progression, like the ones we see here, to calculate the sum of its first n terms, we can use the following formula. S sub n, or Sn, is equal to the first term of the sequence, so that's u1 or u sub 1, times in parentheses r raised to the power of n minus 1, and all of that's written over r minus 1. Now the r that we see here is the geometric sequence's common ratio. And if you're a little unsure of what that is, don't worry, we'll clarify that in just a minute when I work through this first example. One thing that can be a little confusing when calculating sums of geometric sequences is that this formula can also be written in another way. Indeed, we can also write this as u1, the first term, times in parentheses 1 minus r raised to the power of n over 1 minus r. Looking at these two formulae, hopefully you notice that the only difference between the two is the order in which the common ratio r and the 1 appear on the numerator and the denominator. And I'll say right away, regardless of which of these two formulae we use, we'll get the same result each and every single time. So you can't really go wrong regardless of which one you choose. Finally, I should say, this formula only holds, or only works, if the common ratio r isn't equal to 1, since this would lead to the denominator being equal to 0, which we cannot have. All that being said, let me go ahead and box this formula. There we go. Okay, now before I work through this first example here, let me say one last thing about this formula, and that is why we have two different ways of writing it. Well, to put things as simply as I can, we tend to use this second formula that we have here as soon as the geometric sequence's common ratio r is less than 1. Indeed, choosing this formula rather than the first one when the common ratio is less than 1 will allow us to avoid having anything negative on the denominator here. And so that's worth keeping in mind. That's why we have that second formula. All that being said, let's go ahead and start working through these examples. For the first one, we're told, given the geometric progression shown here, where we have 5.1, 15.3, 45.9, and 137.7, we need to find the sum of the first 12 terms. Okay, well, just as I often do, I'll start by writing SOL here for solution, and I'll go ahead and copy these first few terms here. We have 5.1, 15.3, 45.9, and last but not least, we have 137.7. And we have 3 dots which indicate that this geometric progression carries on this way forever. Now, looking at the formula we have for calculating the sum of the first n terms, we quickly see that we need two things, those being the first term, u1, and the common ratio, r. Now, looking at our sequence here, the first term, well, that's quite obvious. That's 5.1. So we already know that the first term, u1, is equal to 5.1. For the common ratio, on the other hand, we need to figure out what we'd have to multiply each term by to get to the next term. And if you're uncomfortable seeing what that number is right away, then it's important to remember that the common ratio r can be found by dividing any term of this sequence by the previous term. So for instance, we could say that r is equal to 137.7 divided by 45.9. Or we could say that it's equal to 45.9 divided by 15.3. And last but not least, we could say that r is equal to 15.3 divided by 5.1. And in fact, I'll go ahead and write that r is equal to 15.3 divided by 5.1. And now if needs be, go ahead and use your calculator to calculate 15.3 divided by 5.1. And if I do so as well, you can see my calculator here. That would be 15.3 divided by 5.1. And I press on enter, and we're done. We can see that the common ratio r is equal to 3. There we go. Okay, now that we've made a note of the first term as well as the common ratio, we're ready to use the formula to calculate the sum of the first 12 terms. And so keeping in mind that the common ratio we have here is 3, which is bigger than 1, I'll go ahead and use the first formula we have here. And I can write that the sum of the first 12 terms, so S sub 12, is equal to the first term, U1, times in parentheses R raised to the power of 12 minus 1, and all of that's written over R minus 1. Now replacing U1 by 5.1 and the R's that we see here by 3, this turns into 5.1 times in parentheses 3 raised to the power of 12. I take 1 away from that, and all of that's divided by 3 minus 1. And at this stage, I could of course plug this into my calculator directly, but I have trouble leaving a 3 minus 1 like this on the denominator. Indeed, since 3 minus 1 is equal to 2, I'll go ahead and write that this is equal to 5.1 times in parentheses 3 raised to the power of 12. I take 1 away from that, and I divide all of that by 2. And now that that's done, I enter all of this into my calculator. And since the numerator has more than one term here, I write all of it inside its own pair of parentheses. So here we go. On my calculator, I'll go ahead and open up a pair of parentheses for that numerator, and I type 5.1 times, in parentheses, 3 raised to the power of 12, so that's 3 raised to the power of 12. I get away from that exponent. I take 1 away from that, and I exit all of those parentheses. That's my numerator taken care of. I now divide all of that by 2. And so I type 2, and I press on Enter. And we're done. Copying the result we see on the calculator, we can now state that the sum of the first 12 terms is equal to 1,355,172. And that's the answer. And there we go. We now know how to use this formula for calculating the sum of the first n terms of a geometric sequence. Before I work through the second example, let me say something. At times, a student or two will ask me why we actually need this formula in the first place. Indeed, since we know the common ratio, we could carry on with this geometric progression and write all the terms we need up to the 12th term, and then simply add them all together. And that would definitely work. Indeed, you could go ahead and do it yourself. You could work out what the next term of the sequence is by multiplying 137.7 by 3, then the next term by multiplying the result you get by 3, and the term after that by multiplying that result by 3, and you could carry on that way all the way up to the 12th term. Then add all the terms you get together, and you'll get the same answer as this. The problem is, though, what if I were to ask you for the sum of the first 25,371 terms? Well, I'm sure you'll agree that it wouldn't be practical to find all of those terms in the sequence. Indeed, it would take you forever to find all those terms, and the chances of making a mistake somewhere along the line would be huge. So it's important to know how to use this formula. That being said, I carry on. For the second example we see here, we're told the first few terms of a geometric sequence are shown here. We have 192, 144, 108, 81, and the sequence goes on forever. And we're told find the sum of the first 15 terms. Okay, well, just as I did for the first example, I'll start by copying those terms. That's 192, 144, 108, and 81. And of course the 3 dots that tell me that it goes on forever. Once more, to use this formula, the first thing I need to make a note of is this sequence's first term. So in this case that would be 192. So that's U1, that's 192. And we also need to find this sequence's common ratio, R. And to find R, remember, if you don't see it right away, you can take any term of the sequence and divide it by the previous term. So 81 divided by 108, or 108 divided by 144, or 144 divided by 192. And so I'll do that. I'll say that R is equal to 144 divided by 192. And now looking at this fraction here, it can be simplified. And to save us a bit of time, I'll state what the common factor is. It's 48. And so getting rid of that common factor, we can state that this common ratio R is equal to 3 over 4, so I'll write 3 over 4, which we could also write as a decimal 0.75. And I'll go ahead and box all of that. There we go. Now I should say, if the idea of simplifying fractions like this one scares you a little bit, do not worry. You could also find this 0.75 directly with your calculator. And in fact, I'll do it on my calculator now. If I calculate 144 divided by 192, I quickly see that that's equal to 3/4, and I can write that result as a decimal. And one way to do that on this calculator is to click on Menu, followed by Number, followed by Convert to Decimal, which is the first option. And I click on Enter. And there we go. As you can see, we get 0.75. Okay, now that we've made a note of the first term as well as the common ratio, we're ready to use our formula. Notice here that the common ratio is less than 1, and so I'll use the second formula we have here. And I'll go ahead and write that the sum of the first 15 terms, S sub 15, is equal to the first term, U1, times 1 minus r raised to the power of 15, and all of that's written over 1 minus r. I now replace the first term here by 192, and I replace the common ratio by 0.75, so this becomes 192 times, in parentheses, 1 minus 0.75 raised to the power of 15. And all of that's over 1 minus 0.75. And now since 1 minus 0.75 is equal to 0.25, I'll go ahead and state that this equals to 192 times, in parentheses, 1 minus 0.75 raised to the power of 15, and all of that's over 0.25. And now that all of that's done, I go back to my calculator and I enter all of this. Remember, I write the entire numerator inside its own pair of parentheses. So I open up a pair of parentheses and I type 192 times, in parentheses, 1 minus 0.75 raised to the power of 15. So that's 15, there we go. I exit all the parentheses and I divide that by the denominator, which is 0.25. And so I type 0.25. I'm happy with all of that, so I press on Enter. And we're done. The sum of the first 15 terms is equal to 757.73686. And if I round my answer to 3 significant figures, I look at the fourth significant figure, which is 7 here, so I round the third significant figure up. And so that would be S sub 15, the sum of the first 15 terms, is equal to 758. And I could specify in parentheses that's rounded to 3 significant figures. And that's the answer. And there we go. We've now used this second formula for calculating the sum of the first 15 terms of this sequence. Once more though, let me insist, it really doesn't matter which of the two formula we use. Indeed, for this first example, I could have used the second formula and I would have obtained the same answer in the end. Similarly, for this second example, I could have used the first formula we have here, and I would have obtained the same answer in the end. In fact, let me quickly solve the second example using the first formula we have here. And I'll do that in gray here. If I calculate S sub 15 with the first formula, that would be U1 times, in parentheses, r raised to the power of 15 minus 1, and all of that's over r minus 1. And so replacing U1 by 192 and the r's that we see here by 0.75, this would turn into 192 times, in parentheses, 0.75 raised to the power of 15, and I take 1 away from that, and all of that would be written over 0.75 minus 1. Now on the denominator we'll have 0.75 minus 1, which will be negative 0.25. And so this will equal to 192 times, in parentheses, 0.75 raised to the power of 15, take 1 away from that, and all of that's divided by negative 0.25. Now moving over to our calculator and typing this entire numerator inside its own pair of parentheses, we'll have 192 times, in parentheses, 0.75 raised to the power of 15, I'll take 1 away from that, and I exit all the parentheses. That's the numerator taken care of. And I now divide all of that by negative 0.25. And I'll type that inside a pair of parentheses, that's negative 0.25. I exit those parentheses, and I press on Enter. And we're done. On our calculator, we can see that that's equal to 757.73686, which is exactly the same result as the one we had found previously. And so hopefully you're now convinced that it doesn't matter which of these two formulae you'll use. It's simply convenient to use the one I boxed in blue when the common ratio is less than 1. And there we go. We now know the formula for calculating the sum of the first n terms of a geometric sequence, and of course, we now know how to use it. And that's it for this tutorial.